Welcome to Real Analysis Advanced Calculus Lecture 6, Section 2.3 of the text Advanced Calculus by Patrick M. Fitzpatrick, the Monotone Convergence Theorem. This is Dr. Gilbert, Eyabi. Now, after studying the convergence of sequences in Section 2.1, we know that we can combine the sum, product, quotient, and constant multiple limit theorems to determine the convergence of various sequences. It is our goal to be able to determine the convergence of more general sequences. So our attention at this point would be turned towards providing certain criteria that would be sufficient for us to determine the convergence of sequences without necessarily knowing the limits of those sequences. In other words, if I give you a sequence AN, you should be able to tell whether the sequence converges or not, even if you do not know the limit of the sequence. Before we get into that, we want to recall that back in section 2.2, we did prove that every convergence sequence is bounded. If you have forgotten, go back and check it out. A beautiful proof. Now, I did ask a question. What about the converse? Can we say that every bounded sequence is convergent? If not, are there conditions that could be added to the boundedness of a sequence to guarantee convergence? Define the sequence an by an equals -1 raised to the power n, where n is a natural number. This sequence is bounded. If n is even, an is 1. If n is odd, an is -1. So the absolute value of an is less than or equal to 1 for every natural number n. An is a bounded sequence, but it is not convergent. It is an alternating sequence. So one more time. Are there conditions that could be added to the boundedness of a sequence to guarantee convergence? Yes, and that would be the monotone convergence theorem, MCT. Before we look at that theorem, let us take some definitions. Subsection 2.3.1 definition. A sequence AN is said to be monotonically increasing or monotone increasing provided that an plus 1 is greater than or equal to an for every index n. For example, define the sequence xn by xn equals 2 raised to the power n. Then xn plus 1 is greater than or equal to xn for every natural number n. It's an abstract class, so let's go ahead and prove it very quickly. For every natural number n, n plus 1 is greater than or equal to n. So this means 2 raised to the n plus 1 is greater than or equal to 2 raised to the power n. And again, that holds for every natural number n. But by the definition of our sequence xn, this would be xn plus 1 greater than or equal to xn. In other words, the sequence xn is monotone increasing. Now, if needed, we would say that an is strictly monotone if an plus 1 is strictly greater than an for every n in n. Similarly, we can define monotone decreasing. We say that a sequence an is said to be monotonically decreasing provided that an plus 1 is less than or equal to an for every index n. Example. Define the sequence xn by xn equals 1 divided by 2 raised to the power n. Observe that xn plus 1 is less than or equal to xn for every natural number n. As before, n plus 1 is greater than or equal to n for every natural number n. And that implies 2 raised to the power n plus 1 is greater than or equal to 2 raised to the power n, and that holds for every natural number n. So if I flip everything, I end up with 1 divided by 2 raised to the n plus 1 less than or equal to 1 divided by 2 to the n. And the left-hand side is xn plus 1, the right-hand side is xn. So we can say that xn plus 1 is less than or equal to xn for every natural number n. In other words, our sequence xn is monotone decreasing. So if I give you a sequence, you should be able to verify whether the sequence is monotone increasing, monotone decreasing, or neither. Again, if needed, we would say that a sequence is strictly monotone decreasing if an plus 1 is less than an for every natural number n. A sequence an is called monotone if it is either monotonically increasing or monotonically decreasing. So if you're told that a sequence an is monotone, it means it could be monotone increasing or monotone decreasing. Here we are, subsection 2.3.2 theorem, MCT, the monotone convergence theorem. A monotone sequence converges if and only if it is bounded. In other words, if an is a monotone sequence, then boundedness implies convergence. Whether an is monotone or not, convergence implies bounded. So the extra condition that is supposed to be added to the boundedness of a sequence to guarantee convergence is monotone. Beautiful. Let's finish the theorem. Moreover, the bounded monotone sequence converges to the sup if it is monotone increasing and converges to the inf if it is monotone decreasing. So let's restate that. If a sequence is convergent, then it is bounded. That is the forward direction. The reverse direction, if a sequence is monotone and bounded, then 1, it converges to the supremum if it is monotonically increasing. 2, it converges to the infimum if it is monotonically decreasing. Let's go ahead and prove that. Okay, the forward direction. Let an be a monotone sequence. Suppose an is convergent, we have to prove that an is bounded. Oh, wait a minute, we already did. Yes, we did prove that if an is a convergent sequence, then an is bounded. So the forward direction is settled, and we would focus on the reverse direction. If you missed that lecture, go back and review the lecture. Reverse direction. Let an be a monotone sequence. Suppose an is bounded. We must prove that an converges to either the sup, if it is increasing, or the inf, if it is decreasing. So let's start off with monotone increasing sequences that are bounded above. So suppose an is monotone increasing and an is bounded above. Define the set S to be the set of all the terms of the sequence an. N is a natural number. Then since the sequence is bounded above, S is also bounded above. Therefore, by the completeness axiom, S has a least upper bound or a sup. Let L be the supremum of S. Our goal would be to prove that the sequence an converges to L. Okay? An is monotone increasing. An is bounded above. We have defined a set S, the set of all the terms of the sequence an. S is bounded, and so it has a sup, and we called the sup L, and we just have to prove that an converges to L. Okay, we make a very serious claim. An converges to L indeed. Really? Let's prove it. Let epsilon greater than 0 be given. We want to find a natural number n such that the absolute value of an minus L is less than epsilon for every natural number n greater than or equal to uppercase N. In other words, I want to prove that negative epsilon is less than or equal to an minus L, which is less than epsilon, or L minus epsilon is less than an less than L plus epsilon for every n greater than or equal to uppercase N. So this is where I am going. Now let's put together some of the things we already have. We know that epsilon is positive, and we know that the supremum of S is L. Now let's start off with the supremum of S. Now the supremum of S equals L implies that an is less than or equal to L for every natural number n. That holds because L is the supremum. Supremums are upper bounds. So L is an upper bound. But since epsilon is greater than 0, L is strictly less than L plus epsilon. It doesn't matter how small epsilon is, L is less than L plus epsilon. In other words, AN is less than or equal to L, which is strictly less than L plus epsilon, and that holds for every natural number n. Call that inequality chain 1. Also, since L is the supremum of S and epsilon is greater than 0, L minus epsilon cannot be an upper bound for S. But what does that mean? It means there is a natural number which we call uppercase N such that L minus epsilon is less than AN, such that L minus epsilon is less than A uppercase N, and call this inequality 2. Now we know that AN is monotone increasing. So for every n greater than or equal to uppercase N, AN is greater than or equal to A uppercase N. In other words, A uppercase N is less than or equal to AN for every n greater than or equal to N. Now let's put our things together. We do know from inequality 2 that L minus epsilon is strictly less than A uppercase N. But A uppercase N is less than or equal to AN right here, and that holds for every natural number n greater than or equal to uppercase N. But by the inequality chain 1, AN is strictly less than L plus epsilon. So AN is less than L plus epsilon. And this inequality chain is possible whenever n is greater than or equal to uppercase N. In other words, L minus epsilon is strictly less than AN, which is strictly less than L plus epsilon for every n greater than or equal to uppercase N. In other words, I can subtract L on all sides and I would get negative epsilon less than AN minus L less than epsilon for every n greater than or equal to uppercase N, and that implies the absolute value of AN minus L is less than epsilon for every n greater than or equal to uppercase N. In other words, by the epsilon n definition of convergence back in section 2.1, AN converges to L, which is the supremum of S. So we found a monotone increasing sequence that is bounded above, and we have just proved that that sequence converges to the supremum of S, where S is the set of all the terms of AN and a natural number. That proves part 1. Part 2, suppose AN is monotone decreasing and bounded below. I need you to construct the proof that AN would converge to the infimum of S. I would leave that as a simple exercise for serious students. Now let's look at a few examples to illustrate what we are doing. Define the sequence Sn by Sn equals summation k from 1 to n, 1 over k times 1 divided by 2 raised to the power k for every natural number n. Prove that Sn is convergent. Proof. Clearly, Sn is monotonically increasing. We are dealing with the sum of positive terms. Observe that everything here is positive, so we are dealing with the sum of positive terms. Therefore, Sn is monotonically increasing. If I can verify also that Sn is bounded, then I can conclude the convergence of Sn without knowing what the limit of the sequence is. Now, k times 2 raised to the power k is greater than or equal to 1 times 2 to the k, and that is because k starts from 1 right up to n. So the least k can be is 1. So this inequality chain is true. We flip everything and end up with 1 divided by k times 2 raised to the power k less than or equal to 1 divided by 2 to the k, and I can hit my summation sign on both sides, and I end up with summation k from 1 to n, 1 over k times 1 over 2 to the k less than or equal to summation k from 1 to n, 1 divided by 2 raised to the power k. Why am I doing so? Because I want to use the geometric sum formula. Observe that the left-hand side is just my nth term of my sequence Sn. So Sn is less than or equal to summation k from 1 to n, 1 divided by 2 raised to the power k, which is the same as summation k from 1 to n, 1/2 raised to the power k. Now, by the geometric sum formula, which is r minus r to the n plus 1 divided by 1 minus r, in this case, r is 1/2. This gives me 1/2 minus 1/2 raised to the n plus 1 divided by 1 minus 1 divided by 1/2, and I do not even have to complete the arithmetic involved here. This would lead me to 2 times 1 divided by 2 minus some positive term. If I open the parentheses, I'll end up with 1 minus some positive term. It doesn't matter how small the positive term is, my difference will be less than 1. In other words, Sn is less than or equal to 1 for every natural number n, i.e., the sequence Sn is bounded above. Therefore, by the monotone convergence theorem MCT, my sequence Sn is convergent. And yes, it converges to the soup. Well, I do not know what the soup is, so I don't have to bother about the limit of the sequence. But I can guarantee that the sequence converges, and that is what this section is all about. Next example, subsection 2.3.4. Define the sequence Sn by Sn equals summation k from 1 to n, 1 over k for every natural number n. Sn looks like the sequence we just defined above, but this sequence is very peculiar. It is known as the harmonic series. As the sequence we just defined above, Sn is monotone increasing, the sum of positive terms. The next question is Sn bounded? You can see the proof on page 40 of our text, Advanced Calculus by Patrick M. Fitzpatrick. There is a detailed analysis of this sequence and the proof that Sn is actually unbounded. Very briefly, from the text, you would see that S2 raised to the power n is greater than or equal to 1 plus n over 2. Let's call this inequality plus. From plus, we can use the Archimedean property of the set of real numbers to conclude that Sn is unbounded, i.e., it follows that Sn is not a bounded sequence. But we do know that every convergent sequence is bounded. So if we find a sequence that is not bounded, we can conclude that the sequence is not convergent. So our sequence, as beautiful as it is not a convergent sequence. Now let's change gears and look at a couple of other proofs from this section. Subsection 2.3.5 proposition. Let C be a real number such that the absolute value of C is less than 1. Then limit as n approaches infinity of C raised to the power n equals 0. In other words, A divided by B raised to the power n always converges to 0 if the absolute value of A is less than the absolute value of B. C cannot be equal to 1 or negative 1. Proof. We shall look at a couple of cases. The first case when C equals 0, the next case when C is less than 0, and then when C is greater than 0. Case 1. C equals 0. If that is the case, then the limit as n approaches infinity of C to the n equals the limit as n approaches infinity of 0 raised to the power n, and that simply equals the limit as n approaches infinity of 0, which is 0. And we're done. Cases 2 and 3, we will do this together. The case when C is positive or when C is less than 0. Now, since the absolute value of C raised to the power n equals the absolute value of negative C, all of that raised to the power n, the case C less than 0 follows from the case C greater than 0. So it suffices to prove only one of them. And in this case, we are only going to prove the case C greater than 0. Now, C greater than 0 and the absolute value of C less than 1, we're looking at sequences like 1/2, all of that raised to the power n, 8/9, all of that raised to the power n, bigger than 0, the absolute value less than 1. We can verify that the sequence C raised to the power n is going to be monotone decreasing. And as a matter of fact, it is also bounded below by 0. By the monotone convergence theorem, Since our sequence Cn is bounded below and monotone decreasing, it converges to L, where L is the infimum of all Cn, where n is a natural number. We just have to prove that L equals 0. If that is the case, then we would have shown that the limit as n approaches infinity of c to the n equals 0. So is L equal to 0? Well, our claim is that yes, L equals 0. Proof of claim. Suppose L is different from 0. Then since c is positive, we would have that c to the n equals c to the n plus 1 divided by c. This is just simple rules of exponents. And this is greater than or equal to L divided by c for every natural number n. L is the infimum. So for every natural number n, c raised to the n is going to be greater than or equal to L. In this case, c to the n plus 1 is greater than or equal to L. And since we are dividing by c, c to the n plus 1 divided by c would be greater than or equal to L divided by c. But what does that mean? I have shown that c to the n is greater than or equal to L divided by c. So L divided by c is a lower bound for our sequence c raised to the power n. But that is a problem because L divided by c is actually larger than L. So we are going to contradict the maximality of L. L is the greatest lower bound. There is no bigger lower bound of our set S. So L divided by c cannot be a lower bound for our sequence c raised to the power n. This is a contradiction which arises from the assumption that L is different from 0. Therefore, L equals 0 and we are done. In other words, the case c greater than 0 has been verified, and since the case c less than 0 follows directly from the case c greater than 0, we can conclude that we are done. So whenever c is a real number and the absolute value of c is less than 1, c raised to the power n would converge to 0. And lastly, we look at subsection 2.3.6 theorem, the nested interval theorem. For each natural number n, let an and bn be numbers such that an is strictly less than bn. Consider the interval in defined by in equals an bn, closed interval. Now assume that in plus 1 is a subset of in for every natural number n. Also assume that the limit as n approaches infinity of bn minus an equals 0. Conclusion. Then there exists exactly one point x that belongs to the interval in for all n, and both sequences an and bn converge to this point x. So let me put together all the facts and what we are trying to prove. Proof. Here is what we are given. Number 1, an is less than bn for every natural number n. Number 2, the closed interval in is defined as an bn for every n in n, and it is a closed interval. Number 3, the interval in plus 1 is a subset of the interval in for every natural number n. And assumption number 4, the limit as n approaches infinity of bn minus an equals 0. Conclusion, required to prove there exists a unique number x in the interval in such that my sequence an converges to x and my sequence bn converges to x. So let's put all these 4 given to come up with what we are required to. Now from 3, in plus 1 is subset of in, we have that an is less than or equal to an plus 1, which is strictly less than bn plus 1, which is less than or equal to bn. That is what 3 means. In other words, an is less than or equal to an plus 1. What does this say about the sequence an? It is monotone increasing and it is bounded above. by B1. Observe that none of the ANs would be greater than any of the BNs. So in particular, all the ANs are less than or equal to B1. So AN is a monotone increasing sequence that is bounded above by B1. Therefore, by the monotone convergence theorem MCT, AN converges to some number A, which happens to be the supremum of the set of all the terms of AN, where n is a natural number. In other words, AN is less than or equal to A for every n in n. A is the sup, so AN is less than or equal to A. Call that inequality 1. By a similar argument, right here, Bn plus 1 is less than or equal to Bn. That concludes Bn as a monotone decreasing sequence which is bounded below by A1. None of the Bn's will be less than any AN. So in particular, all the Bn's are greater than or equal to A1. In other words, Bn is a monotone decreasing sequence that is bounded below by A1. And therefore, by the monotone convergence theorem, Bn converges to some number B, which happens to be the infimum of all the terms of our sequence Bn, where n is a natural number, i.e., Bn is greater than or equal to B for every natural number n. Call that inequality 2. Now let's go back to the fourth assumption. The limit as n approaches infinity of an minus bn is 0. In other words, 0 equals the limit as n approaches infinity of bn minus an, and that equals the limit as n approaches infinity of bn minus the limit as n approaches infinity of an. But the limit as n approaches infinity of bn is b. We just proved that bn is decreasing bounded below, so it converges to the infimum b. The limit as n approaches infinity of an is a, so all of that equals b minus a, i.e., 0 equals b minus a, or we will say that a equals b. So set our x to be a, but since a equals b, x equals a, x equals b. In other words, both sequences an and bn converge to the point x. But we are not done yet. We have two more things to verify. Number one, we have to verify that the number we just found, our x, is actually an element of the closed interval In. And number two, we have to verify that x is unique. There is only one such x in that interval. Now, an and bn are sequences in In, which is the closed interval an, bn. And an converges to x, bn converges to x. And we did prove in previous lectures that if a sequence an is in the closed interval ab and the sequence converges to some point, that point also belongs to that closed interval. So this is a closed interval, and an and bn are sequences in this interval. They both converge to x, therefore x is an element in the closed interval an, bn, and that takes care of the fact that x is an element of In. Now, can there be more than one such values? No, there can only be one such point in the interval In. Why? Because the existence of two would contradict the assumption we have in 4 above. The limit of the difference is 0. Therefore, if conditions 1, 2, 3, and 4 hold, we just proved that, number one, there exists a unique x in the interval In such that both an and bn converge to x. 4 things. And that brings us to the end of the proof and the end of section 2.3. And I look forward to seeing you in lecture 7. Thank you and God bless you.